The Pythagoras theorem is probably the most basic and well-known theorem of Euclidean geometry and lies at the base of all other subsequent developments relating to trigonometry or Cartesian geometry. We all learned it in school, and it just says that if we have a right triangle, a triangle in which one of the angles is a right angle, the hypotenuse, which is the long side opposite the right angle, if we take this, the hypotenuse and put a square upon that side, and take the squares erected on the other two sides, here in the picture CB and CA, then the sums of these squares is equal to the square on the hypotenuse. Everyone knows that. We all learn it in school. And we've all learned many different, and there are many different proofs, quite elementary, using constructions of Euclidean geometry with triangles and squares and a variety of ways of doing it. But one method which is perhaps less known dates back far before the time of Pythagoras to about 4,000 years ago, and an indication of it can be found on a cuneiform clay tablet of the Sumerian Babylonian type, dating back to very ancient times. And the idea of the proof is given on the cuneiform, on the cuneiform tablet, just by a picture. There isn't a detailed discussion, but from the picture we can reconstruct a very interesting other proof, which is quite distinct from the usual finite proofs, because it involves subdividing the triangle into an infinite number of similar subtriangles and looking at the subdivision of the sides that result and adding up the segments to obtain the full length of the hypotenuse or of the base by using the very simple formula that gives the sum of a geometric series. So the details of this are not provided, of course, in this cuneiform tablet, but we can reconstruct it if we just give a proper interpretation of the picture that is provided. So in this picture, I've added labels, and so the triangle is ACB with the vertex C where the right angle is, and AB the hypotenuse. And the lengths of the sides are the lengths of CB is little a, AB is little c, and AC is little b. And the construction consists of taking the point C, dropping a perpendicular to the hypotenuse, where it meets it in one point, and then again dropping a perpendicular to the base, and continuing, going back to the hypotenuse, alternating between the two sides, always with right angles on the point of meeting, to form a zigzag decomposition of this triangle into a union of triangles that are all of the same shape. They have the same angles, so they're all similar triangles. And then the Pythagoras theorem, which is c squared is equal to a squared plus b squared, can be derived from this construction by just adding up the lengths of the segments which we have created by the subdivision. So here is a detailed explanation of this proof with labelings attached. So let's denote the vertices A and C also as C0 and A0, because we're going to be adding similar labels for the other points. And then the successive labels, where we've dropped a perpendicular from C to the side AB, we'll call the point of contact capital C sub 1, and the next one where we drop the perpendicular to the base we'll call capital A sub 1, and then C sub 2, A sub 2, and so on. So that gives this sequence of labels, which are all points along either the hypotenuse for the C or along the base for the A's. And let's also label the lengths of the line segments between consecutive such points using a lowercase c. So the line from ci minus 1 to ci has length little ci, and the line segment from ai minus 1 to ai has little ai. So for example, if I is 1, then this is C0, C1, that's this segment C0, C1, that has length C1. The next one is the segment from C1 to C2, and that has length little c2, and so on. And the same for the A's. The segment from A0 to A1 is labeled as length little a1, the next one little a2, and so on. So now if we look at the sequence of triangles, beginning with the original triangle, ACB, we'll call T0. And then the successive triangles, the next largest is the one where we're connecting these three vertices, C0, A0, and C1. We'll call that T1. And the next one with C1, A0, A1, we'll call T2, and so on. So the odd-numbered triangles, T2i minus 1, for I going from 1 to infinity along the integers, are the ones with vertices ci minus 1, ai minus 1, ci, and the even ones are the ones with vertices ci, ai minus 1, and ai. All of these are similar, but their orientation alternates. So the upper one has the opposite orientation from the lower one, upper, lower, upper, lower. They alternate in orientation, but the angles are all the same. Moreover, the ratio between all of these is equal. They have a common ratio. The ratio between T0 and T1 is not the same. It's the ratio between T0 and T1 is the same as the ratio between the hypotenuse and the height b. So that's c to b, but all of the subsequent ones between T1, T2, T2, T3, and so on are of the ratio equal to c over a, so 1 over r, where r is the ratio of a to c. So these have a common ratio, and they're all descending by the same factor r. That means that if we just compute successively the values of C1, B, C2, A1, A2, C3, A3, C3, and so on, we find the following expressions. For I equal to 1, the exponent here is 0, and so we just have b squared over c. So little c1 is just b squared over c, which is b, the hypotenuse, multiplied by the ratio between the big triangle ACB and the smaller triangle ACC1, which is b over c. So that gives you a b squared over c for the first term in this sequence. And from there on, the ratios are all a factor of r, which is a over c, times the previous one. So c1 is b squared over c. A1 is c1 multiplied by r. So that would be I equal to 1. If I is 1, this is r to the power of 1, so it's b squared over c times r. And then we go back from A1, we go to A2, we get another factor of r, and the general formula goes up by powers for the ci's by powers of r squared, and for the ai's for powers by r squared. But alternating between the two, it's always the same ratio r. So now we take these expressions for the segments that are formed along the hypotenuse and along the base, and we add them up. And they, of course, must add up to the length of the hypotenuse and the length of the base. So we have the following sum. We sum all of the CIs, and that is a geometric series with common ratio equal to r squared. It's equal to b squared over c times r to the 2i, so that's r squared to the I, summed from I equals 0 to infinity. And there's a very simple formula which gives this geometric sum. It's just equal to 1 over 1 minus r squared. So the total expression is b squared over c times 1 minus r squared, We can simplify that a little bit by using the fact that r is a over c, so we substitute a over c in here, multiply through by c squared, and cancel common factors, and we get this as the answer, b squared c over c squared minus a squared. And that must equal c. We do the same thing for the base, sum up the ai's. Here we have one more factor of r, because it's going from when it goes from 1 to infinity, that's the same thing as one higher power going from 0 to infinity. So we start out with b squared over c times r, and then subsequently multiply by these factors of r squared, add it up. We again have a geometric series with common factor r squared, but the first term, instead of being b squared over c, it's b squared r over c. So the final sum, the resulting sum, is b squared over c times 1 minus r squared. And r again is a over c. We substitute that, simplify by multiplying through by c squared, and the expression becomes b squared a over c squared minus a squared. And that must equal the base length, which is a. So both of these equalities, in fact, are the same thing. Here we can cancel out the c on the left and on the right and obtain 1 is equal to b squared over c squared minus a squared. Here we cancel out the a on the left and the right, and we also get 1 is equal to b squared over c squared minus a squared. And multiplying through by the denominator and bringing everything to one side, that is exactly the same as a squared plus b squared equals c squared, which is the Pythagoras theorem.